Question number 5 deals with the method of Frobenius to obtain, here we have a second order ODE. So we're looking for two linearly independent solutions. But with the method of Frobenius, it may give us solutions that are not a power series, but are similar to a power series. The difference is that here we might end up with fractional exponents. With our power series solutions, like the previous two examples, all of our exponents were whole numbers. Here we can end up with negatives, and we could also end up with fractions for exponents. So the difference is that when we substitute in, we're choosing the sum n goes from 0 to infinity c sub n x to the m plus r. And then when we calculate the first and second derivative, we have to keep that lower index at 0. With the regular power series, we could have left it at 0, but the first terms of both of those series was 0, and so we could just take that out and simplify things. Here we can't. Also, here we'll have an r that we need to solve for, and then we'll use that r value to create a recurrence relation for each of our linear independent solutions. Okay, so let's see what we have. I'm going to substitute in. We get 4x times y double prime. Y double prime is the sum as n goes from 0 to infinity c sub n times m plus r times m plus r minus 1 x to the m plus r minus 2, and then minus y prime, which is the sum n goes from 0 to infinity c sub n times m plus r times x to the m plus r minus 1, and then plus 4y, which is the sum n goes from 0 to infinity. Just going to draw a line here. C sub n x to the m plus r equals 0. We have the same rules for combining summations that we did before. That if you have any x's outside of the summation, those x's come in and they get combined with the x that you have inside the summation. So in that first term, I'm going to take away this x outside and then increase that power of x by 1. This first term becomes the sum n goes from 0 to infinity c sub n times m plus r times m plus r minus 1 times x to the m plus r minus 1. My other two terms I just copy. Minus sum n goes from 0 to infinity c sub n times m plus r times x to the m plus r minus 1 plus 4 times sum n goes from 0 to infinity c sub n x to the m plus r equals 0. Cool. So we brought all the x's inside of the summation. The next step was to look at the exponents, and you want the exponents to be equal. Notice that we have an m plus r. The other ones are m plus r minus 1. So just like before, where we wanted all of our exponents to be k, here we want them to be k plus r. And so on that last summation, we could just replace the n with k, and that'll fix it. On these other two summations, if you let k equal n minus 1, then n is going to be k plus 1, and we can make that substitution. And that's the same for both of these summations. And so I'll go ahead and make those substitutions to get 4 times the sum. So let's see, if n is 0, then k is going to start at -1 to infinity c sub n, which is k plus 1, times n, which is k plus 1, plus r, times, let's see, n minus 1 is k. So this will become k plus r, x to the k plus r, minus the sum. K goes from, so n starts at 0. 0 minus 1 is -1 to infinity c sub n, which is k plus 1, times m plus r, that's k plus 1 plus r, x to the k plus r. And then on the last summation, you just replace the n's with k. K goes from, you have 4 times the sum, k goes from 0 to infinity, c sub k, x to the k plus r equals 0. Okay, so now we have a common power of k plus r. If you look at the lower indices, we have k equals 0, k equals -1, k equals -1. We want to remove terms so that our lower indices match. So I'm going to remove k equals -1 from these first two summations. Let's remove. And when I remove that, let me also do it here. I like to show where these terms come from. So my first term, removing k equals -1, I have the 4 outside. This is going to be a c sub 0, and k is -1, so -1 plus 1 will cancel to give me r, and k is -1, so this becomes -1 plus r, and my exponent becomes x to the -1 plus r. And I'll be able to write my summation now using a lower index of 0. Otherwise, everything just gets copied. So on the second summation, removing k equals -1 gives me c sub 0. And again, -1 plus 1 cancels, so I have r, and then x to the -1 plus r, plus, or not plus, but minus. And I think I can fit this here. K equals k equals 0, because I've taken away the -1 term, to infinity, c sub k plus 1 times k plus 1 plus r, x to the k plus r, and then the last term I'm just going to copy, plus 4 sum, k goes from 0 to infinity, c sub k, x to the k plus r equals 0. Okay, so now I'm going to combine those terms that I took out of the summations together. And all of my summations will have a common x to the k plus r that I'll be able to factor out, just like we did with just the general power series solutions. So let's see, let's pull those terms together from outside, and that gives me 4C0R. I'm going to write that negative 1 plus r as r minus 1, x to the r minus 1. And then my second term that I pull out, minus C0R x to the r minus 1. And then everything else I'll combine into a single summation where I have k goes from 0 to infinity, and I have that x to the k plus r in common. So that's going to give me a 4 c sub k plus 1 times k plus 1 plus r times k plus r. From my second summation, I'm going to have a minus c sub k plus 1 times k plus 1 plus r. And from my last summation, I'm going to have a plus 4c sub k braces equals 0. All of that's equal to 0. Let's see what I can simplify. So from this term that I pulled out of the summation, I have a C0 and R and an x to the r minus 1 in common. I'm going to factor those out. C0R x to the r minus 1, and that will leave me with 4 times r minus 1 and then minus 1. I can simplify that. That's 4r minus 4 minus 1, or 4r minus 5. So let me just go ahead and do that. And then plus, and let's look at our summation. I don't know if I want to combine anything right now or not. We have 3 terms. Doesn't look like we have anything in common because that last term is just 4 times ck. And I do have a 4 in the first term, but I do not in the second term. So there, I'm just going to copy it and carry it down. So luckily here I can just copy and paste, so I don't make any copy errors. Paste it there, and then we'll paste it again here. There. And this is going to give us our recurrence relation. Along with this is the coefficient of the x to the r minus 1 term. And then when k is 0, we're going to have x to the r terms here. And then k equals 1, increase the power by 1, and so forth. And we know that everything is 0. So just like before, all of our coefficients have to be 0, which tells us that our coefficient here, notice we get c sub 0 times r. I'm going to keep that x to the r minus 1 out of it because I just want the coefficients, times 4r minus 5 has to equal 0. That tells us that c of 0 is equal to 0, or r is equal to 0, or 4r minus 5 is equal to 0. So if you take r is equal to 0 as a value for r, and substitute the r equals 0 into that recurrence relation, that's going to give us one of our power series, or one of our solutions. Actually, in the term of power series, because r is just a whole number. If you take from 4r minus 5 equals 0, we get r is equal to 5/4. And so if you take r equals 5/4 and substitute it into that power series, or what looks like a power series, then notice that if r is 5/4, you're going to get x to the k plus 5/4 as the exponent. K is a whole number, so you're going to get, your first term in the summation is going to be x to the 5/4. And then your second term is going to be x to the 9/4, 5/4 plus 1, and so forth. You get fractional exponents. Okay, so we're going to choose, because we have the or here, we're going to choose not to let C0 equals 0, because that would just give us 0 as a solution. We're going to choose r equals 0, and r is 5/4. If I take this recurrence relation and solve it for the highest index, oh, look, we have two of those. My highest index is c sub k plus 1. So if I bring that c sub k term over to the right side, I'm going to have, and if I factor out from these two terms, let me do this first. Let me set this equal to 0 for c sub k plus 1 times k plus 1 plus r times k plus r minus c sub k plus 1 times k plus 1 plus r plus 4 c sub k equals 0. And if I combine these two terms, then notice we've got that c sub k plus 1 times k plus 1 plus r in common. Factoring those out leave us with 4 times k plus r minus 1. And I'm going to bring that c sub k to the right side, equals negative 4 c sub k. So now I can solve for c sub k plus 1, and I get negative 4 c sub k divided by k plus 1 plus r times, simplifying here, we get 4k plus 4r minus 1. 4k plus 4r minus 1. Oh, and this is true for k equals 0 to infinity. 0, 1, 2, and so forth. So we'll do a few terms, 2 or 3 terms from each of our solutions. We have solutions when r is equal to 0 or r is equal to 5/4. We'll do the nicer one first. We'll do r equals 0. When r is equal to 0, we get, our recurrence relation is going to be c sub k plus 1 equals negative 4 c sub k divided by, and r is going to be 0, so those r terms will drop out. We get k plus 1 times 4k minus 1. And that's true for k equals 0, 1, 2, and so forth. So let's find a few terms. Let's start with k equals 0. We'll get c sub 1 equals negative 4 c sub 0 over 0 plus 1 is 1, and 4 times 0 minus 1 is negative 1. So that's just 4c0 is c1. c1 is 4 times c0. And then when k equals 1, we're going to get, again, substitute here, we get c sub 2 equals negative 4 c sub 1 over 2 times k is 1. So I get 4, take away 1 is 3. There I can cancel the 2 with the 4, and I get negative 2/3 c1, but c1 is 4c0. So that gives me negative 8/3 c0 equals c2. And I'm just going to do one more term to get c3. c3 is going to be negative 4 c2 over 4 times, let's see, 4 times 3 is 12, take away 1 is 11. There the 4's cancel, and we get negative c2. c2 is, so let me see, negative 1/11 times c2. c2 is negative 8/3 c0. So that gives me 8/33 c0 is equal to c3. So let's see what this solution looks like. So for r equals 0, remember that our solutions look like this. The sum as n goes from 0 to infinity, c sub n, here we have c1, 2, and 3, x to the n plus r. In this case, r is 0, and so we just have c sub n x to the n. So this is just our power series solutions. So r equals 0, which means that we get y equals c sub 0 plus c sub 1 times x plus c sub 2 x squared plus c sub 3 x to the third, and I'll just say, and so forth. In this case, we said c sub 1 is 4c0. So c sub 1 is 4c0. C sub 2 is negative 8/3 c0. C sub 3 is 8/33 c0. And notice that we only have one variable here, just the c0, that we can factor out. And we'll call that y1 is c0 times 1 plus 4x minus 8/3 x squared plus 8/33 x to the third. And I don't know if it's alternating terms because the signs, because the first two terms are both positive, and so forth. Actually, yeah, we'll call that y1. y1 is actually what we have in parentheses here. But either way, I'm not going to put y1 both places. So I'll just keep it like this. That's one solution. And then our second solution comes from the R value of 5/4. So if R is equal to 5/4, then our recurrence relation, I'm just going to copy this. Then our recurrence relation becomes -4 C sub k over k plus 1 plus 5/4 times 4k plus 4 times 5/4 minus 1, which is going to simplify to -4 C sub k over, let's see, 1 times 5/4 is 4/4 plus 5/4, or 9/4. And on that second parenthesis, you can cancel those 4's. So you get 4k plus 5 minus 1. Oh, nice. 4k minus 4. We can factor that 4 out. And I'm not going to reduce the 4, but I'm going to factor this 4 out to give me a k minus 1. And I'm going to put it in front of the k plus 9/4 so that I can distribute and I won't have to work with fractions. So we get C sub k plus 1. Well, we'll still have fractions, but we won't have fractions within fractions. 4k plus 9 times k minus 1. That's true for, this was k equals 0, 1, 2, and so forth. Yep. And we'll do 3 terms like we did before. So when k is 0, let me see what else I have here. Nothing. I don't have anything. Okay. So when k is 0, we get C sub 1 is -4. Just a minute. I forgot that C sub k in the numerator. So I get -4 C sub k over, or let me fix that, C sub 0 over, when k is 0, this k term drops out, and I get 9 times -1. So that gives me 4/9 C0 equals C1. We'll box that up. When k is 1, I get C sub 2 equals -4 C sub 1 divided by, let's see, k is 1, so this is 4 plus 9 is 13. Uh-oh. And 1 take away 1 is 0. That's undefined. Did I make a mistake somewhere? Let me see. I did, because you should not get an undefined term. And here's where my mistake is, right here. That you probably already saw it. But 4k and then plus 5 take away 1 is 4. That should be a positive 4. And so this should be a positive 1. And so this should be a positive 1. And so this should be a positive 1. And so that should be a negative 4/9 C0 is C1. And that should fix our mistake. Okay, and then down here, 1 plus 1 is 2. So that's times 2. And I can reduce the 2 with the 4 to give me 2. I'll get negative 2/13 times negative 4/9. Wow. C0 is 8. What's that? 27 over 117. C0 equals C2. Wow. And we'll do one more term. So K equals 2 will give me C3 is negative 4 C2 over K is 2. So 4 times 2 is 8 plus 9 is, 17. And then 2 plus 1 is 3. 17 times 3 is 51. And C2 is 8 over 117. C0. 117 was 13 times 9. So nothing is going to reduce. We're going to get negative 32 over whatever 117 times 51 is. That's 85 and 5 is 7, 6, 9. 5967. Wow. C0. That's C3. I'm glad I'm not going to any further steps there. So in this case, our summation looks like this. I'm going to copy this. And here we have R is equal to 5/4. So I'm going to take that summation and I'm going to factor out the x to the r, just make it a little bit easier to calculate. So that the sum as n goes from 0 to infinity, c sub n x to the n is just our power series. And we're going to end up, when r is 5/4, with x to the 5/4 times, and then when n is 0, we get c0 x to the 0, plus when c is 1, c1 x to the first, plus c2 x squared, plus c3 x to the third, and so forth. And so I just have to substitute in my values. Here again we have a C0, and then x to the 0 is just a constant, plus C1 is negative 4/9. C0 x, and then C2 is 8 over 117 C0 x squared, and then C3 is this negative 32 over 5,967 C0 x to the third. And they look like they alternate terms, but I'm not sure. So this is our second solution. If I factor out those C0s, and I guess I'll multiply through by this, x to the 5/4, so that you can see what our second solution looks like. So factoring out the C0, I'm going to get 1. This is a 1. So I'm going to get 1 times x to the 5/4 minus 4/9 x to the, and I'm adding 1, so I'm adding 4/4 to the 9/4 plus 8 over 117. Just add 1 to the previous exponent, x to the 13/4 minus 32 over 5,967, x to the, that should be a 4, 13/4, and then adding another 4 to the numerator, we get 17/4, and then that continues. So these, again, in the parentheses, those are our linearly independent solutions. It doesn't really matter that each one is multiplied by C0. If you write this as a general solution, you're going to say it's C0 y1 plus C, or actually let me fix this a little bit better. Yeah, let's fix it like this. C1 y1 plus C2 y2, where this is my y2, and if I come back up here and erase that y1 there, then this part is my y1. So we have our general solution. I'm not going to write it out. In this question, it asks for 2 linearly independent solutions, and that's what we came up with. And so I will stop recording. That's a long enough video for number 5. And I'll be back with chapter 7. Bye-bye.